and has slowly worked his way up to the University of California at San Diego, where he stops in Atlanta, St. Louis. He's written way too much stuff to even think about trying to tell you about it. The occasion for this one is largely that the graduate students have just finished reading a book where this is part of the topic. So you guys should have lots of questions. Bill?
Thanks, Bob. Okay, what I'm going to do in this talk is first introduce the idea of dynamic mechanistic explanation, which is a hybrid between what has been called the new mechanistic philosophy of science by Rob Skipper, who isn't here right now, and dynamic systems kinds of approaches. And I will use as an exemplar in the latter part of the talk of why one needs to blend dynamics and mechanism. I'll use as the exemplar endogenous activity in brains, particularly some work that's come out in the last 10 years that's just revealing how much brains are actually dynamically active on their own, perturbed by stimuli from the environment, but that isn't the core operation that we need to understand if we're to understand mental activity. So the structure then is I will start with a bit on the new mechanistic philosophy of science and its relation to psychology, dynamical systems viewed as a competitor to the mechanistic approach, then characterize the hybrid, turn to some background on endogenous activity in brains, and then finish with some ideas about what a philosophy of science that would be like that's adequate to this kind of endogenous activity in brain systems. So let me get started. For those who have been in the seminar on my book or taken courses with Rob or Bob, mechanistic philosophy of science is not something new to you, but I will say a little bit for those for whom it is a different framework. A different framework from the one that was dominant in 20th century philosophy of science, where for much of the most accounts of explanation put a strong emphasis on laws as the key element in explanation, and one of the most traditional models of the 20th century for explanation saw explanation as a matter of a logical derivation of the characterization of the phenomenon to be explained from laws and initial conditions. The problem, it's a problem Bob and I encountered back in the 80s when we were trying to flesh out a consequence of this view, reduction as characterized from within this perspective, for examples in the biological sciences, that there just don't seem to be many things that fit the role of laws in the biological sciences or in psychology. There are, to be sure, things called effects in psychology, which look much like laws, but rather than providing the basis for explanation, they rather characterize the phenomenon in need of explanation. So this classical picture doesn't seem to fit well with the life sciences. One option at that point is to say, well, biology, psychology, they just aren't real sciences. That seems a rather strange attitude to take, given how much we have learned from them. Another is to say we need a different kind of framework for thinking about explanation. And if you attend to even the language of almost anybody in the life sciences when they're offering an explanation, the word that keeps cropping up is the term mechanism. What's the mechanism for this phenomena that we are interested in? Well, here's the characterization I tend to work with, or have worked with. You'll see that I want to modify it at this point, but have worked with, and it's not a definition, but simply a characterization of the kind of thing a mechanistic explanation is supposed to involve. A mechanism is a structure performing a function and then the key elements in virtue of component parts, component operations, and the organization. So if one wants to understand how the heart figures in circulating in the blood, one needs to identify the relevant parts of that system, the chambers of the heart, the muscles of the heart, the valves of the heart, characterize what each of them does, and then understand how the system is organized both spatially and temporally so as to achieve circulation of blood. So the basic way to think about developing a mechanistic explanation is that a first and critical task is to delineate what it is that you're trying to explain, what the phenomenon is. That's not trivial. Much research typically has to go into establishing the nature of the phenomenon, and often your characterization of it will change radically as you go forward in developing an explanation. But once you have identified a phenomenon and have a target mechanism in mind, the next challenge is to figure out, well, what are its components parts, what are the component operations within the mechanism. Both of those require not just conceptual advances typically, but also the right kind of intervention tools to cleave the mechanism into relevant parts, and even more challenging, to figure out what operations are being performed. And then, what's often only partially done, begin to understand how these are organized and orchestrated to produce the phenomenon of interest, and to resituate the mechanism back in its environment, to understand how, in fact, it's interacting with the environment in generating the phenomenon of interest. Now, let me just highlight here, and I'll come back at the very end if there's time to elaborate on in a different light, some of the main differences between a mechanistic and a deductive nomological explanation. One is that visual representations are a very natural way to represent mechanisms, not a very natural way typically to represent laws, but in fact visualizing the mechanism in a diagram often plays an important role in one's thinking about the mechanism. When one wants to explain how the phenomenon is generated by the mechanism, typically what one's going to need to do is to, in some way or other, simulate the operation of the mechanism. That may be mentally rehearsing how the operations are being performed, or computationally, developing mathematical equations that characterize each of the parts and characterize how they're interacting with each other. This contrasts rather dramatically with the emphasis on logic playing the role of allowing us to derive a statement of the phenomenon from the laws that are to explain it. Reduction on the classical phenomenological model has been characterized as involving the derivation of laws of one science from those of more basic sciences. Here we're not talking about derivation at all, but decomposition is often characterized as reductionistic. You're taking a system apart, identifying its constituent parts. It could be performed iteratively if there's a need to do so, so that one could be going to smaller, lower level components. But that need is counterposed with the need to recompose the mechanism. There is no privileging of one level in the mechanistic account. One is getting different information when one understands what the components are, how they're behaving, and how the whole mechanism is organized and situated back in an environment to produce the phenomenon of interest. Lastly, within the classical Vienna account, advocates repudiated any role for a logic of discovery, left it often for psychologists to figure out how it is that people made discoveries. But within the mechanistic framework, there are a host of heuristic strategies that one can identify that are probative for taking mechanisms apart, figuring out what the components do, understanding how they behave. So that I think there's a lot to be said about discovery from within the mechanistic framework. Now, to apply this framework to contemporary psychology, typically in a cognitive task, what one is going to do is characterize the operations in terms of information processing. That often involves positing representations, which then become transformed by the operations within the mechanism. There is, and I'm not going to talk about it, though I did spend some time in the book talking about it, a challenge often to figure out just what are the operations of relevance in psychological accounts. often the characterizations of mechanisms are couched at either too high or too low a level. Either they're couched at the same level as the phenomenon itself, just telling us